So, kind of short reminder. So, last time we defined p-adic numbers, and these are an extension of rational numbers. And we saw that these correspond to the set of actually let me not write this. So, QP. So, this is an extension of Q, which is complete with respect to p-adic metric. And this is a property, but also like the property is there just by definition, because last time we defined them as the completion of Q with respect to this metric. Okay, so and this and then we defined, so and then we saw that every element of this set, every p-adic number can be written as a p series, which is so we start with some coefficient. So, there is a0 p to the minus r, and then the next term is some a1, and now I increase the power of p by 1 plus a2 and ak p to the minus r plus k, and this and so on. So, this is an infinite series. So, and these a naught are in the set 1 0 1 p minus 1. So, they are numbers smaller, the integers smaller than p, and so we can represent every p-adic number in such a way, and this allows us. So, last time we defined p-adic valuation, but that was defined on rational numbers. So, this allows us, so this form allows us to extend it to all p-adic numbers. So, Vp of
so in a p-adic number, can there be finitely many of these coefficients non-zero?
yes, that will just correspond to a rational number. So,
okay.
yeah, yeah.
Oh, okay.
So, this is an extension. So, ak what we are saying is ak can become 0 after some maximum value. Okay. So, Vp of this number, let me say, let me name it as q, is minus r. So, it is the coefficient is the power of the smallest power of p that exists in this, that appears in this series, and kind of. So, this is so, and similarly I can define a distance between any two p-adic numbers. So, let us say q1, q2 is p to the minus Vp of q1 minus q2. So, yeah. So, and this is so again this is something a bit different from what happened with real numbers. There, when we do the completion, we have a notion of distance, but this distance takes values in real numbers. This does not happen here. So, we have a distance which we define on the whole on the whole of p-adic space of p-adic numbers, but it still take values in rational numbers. And so this has to be the case because there is no intrinsic ordering on p-adic numbers, but there is an ordering of rational numbers. So, when we say that the p-adic distance between 2 points is greater or less than something, but we are talking about the ordering in rationals, and there is no ordering on p-adic numbers themselves. Okay. So let me go to the next thing, which is, so I also defined ZP, which is just points in QP with the p-adic valuation greater than or equal to 0. And it's, I guess, pretty easy to see that this space is also complete with respect to p-adic matrix because of this greater than or equal to condition. So, what I want to start today with is mostly kind of an interpretation of this space, right? So, an element here, an element in ZP can be written as a series but this time this R must be greater than or equal to 0. So, I can just say A naught plus A1 P plus A2 P square and then AK. And what I want to do is kind of like give an alternative interpretation of this space that goes through finite groups or rings of integers modulo n. So, let us kind of like, so we can step back. So, last time we defined what it means to be a ring, right? And I will not write the definition here, but let me give you another example of a ring. And so, so integers modulo n so they form a ring which we called Z mod n. I think at some point I'm going to slip and write this as Zn and confuse that with Zp, but hopefully I will not. Okay. So there is this, and so where the addition and multiplication are, so A plus B is A plus B mod n, and AB is similarly AB mod n. So, I can think of them as integers, but I identify all integers which differ by a multiple of n to 0. So, this is again, I can think of this as integers, but with the but with an equivalence relation which says that all multiples of n are equivalent to 0. And so, this ring, so this generally has addition and multiplication, subtraction also works, but division generally does not. And the reason it does not work is due to factor that n can have non-trivial prime factors, right. So, if n is equal to PQ with, let us say, PQ greater than 1, or maybe like, just to be very pedantic, the absolute values are greater than 1, then PQ is equal to 0 mod n. So, I cannot have an inverse for either P or Q in this case. So things are simplest for the case when n is a prime. In that case, where should I go? Okay, we'll come here. So in the case where n is a prime, I cannot have this problem because p is a prime. So it cannot be written as the product of two numbers whose absolute value is bigger than 1. And similarly, there is an identity, I think it's called like Bezout's identity, which says that if we have coprime numbers n and p, there are m and q such that m times n plus p times q is 1. So what this means is that if I reduce this equation modulo n, what this tells me is that m n, so this is a multiple of p, is 1 mod n. And if p is a prime, every number in from 0 to p minus 1 is co-prime to this is p. So then every number from 0 to p minus 1 is co-prime to p, and so every number has an inverse unless has an multiplicative inverse unless it is 0. So this z mod p is a field. And in general, maybe these rings can look complicated, but what's less complicated than the general case? So z mod p square is not a field, but so the elements for this happens that p q is equal to 0, although p and q themselves are not 0, are called 0 divisors, and but only 0 divisors are multiples of p. And this is true for all, same is true m is true for all z mod p to the L. So whatever integer L I pick, the only 0 divisors will be the ones which are multiples of p. Okay. So and this operation, let me do. So this operation, so we have a map. So no, the opposite, and an integer m goes to m mod p to the L. And so the question I want to ask is, does this map make sense for rational numbers, right? So and a priori no, right? So if we have, so does this map makes sense for q, right? So can I change this z to q? And the answer in general is no, and the problem is these 0 divisors. So generally no, and the reason is, so because if r is q over p to the k for some k, I do not know we run into problems. But if R is, let us say, Q over S with S co-prime to P, I can define R mod P to the L to be just R mod. So, this is P to the L, and I will multiply it with S inverse mod P to the L. And this is a pretty natural way of trying to extend this map, but this does not work if S does not have an inverse mod P to the L, and that is the case for us when we have a multiple of P.
Do you mean you want to say Q mod PL?
Yes. Yes, Q. Thank you. Yeah. So, in this case, so I can still make sense of this map, and but not for all the rational numbers. So, but it makes sense for a subset, and this subset is actually quite nice. And so, I will just define Z tilde P to be all rational numbers. So, how did I write Q over S and Q S are integers, but S, so GCD of S P is 1. And so this looks almost like what we did when we defined rational numbers. Those were tuples, two tuples of integers, and there was a relation. That relation is still there, because I am writing this Q over S as a rational number. The only new thing is this GCDCP S and P is 1, and what it says is I do not want any factor of P in my denominator. And I can remember that Q over S plus Q prime over S prime was S S prime denominator, and then I had Q S prime plus Q prime of S. So, if S and S prime do not have any factor of P, then this will also not have a factor of P. And I can do the same. Q over S times Q over S prime is Q Q prime over S S prime. So, the multiplication also works nicely in this set. So, this set, so Z tilde P.
Is it Z tilde P or PL?
No, this is just Z tilde P. And on this set, like on this set Q mod P to the L still makes sense for all L, right? I can still take reduce these numbers modulo P to the L for all L. But even if I have even if I have a single degree of P here, I cannot do that, because P is a 0 divisor in P model. Okay. So, I have this. So, this Z tilde P is subring.
No, wait. So Z tilde P. So you're making the rationals
No, no, no. So these are just integers. So q and s are just integers, and the denominator is co-prime 2.
So you're just doing it generally?
Yeah.
General integers.
So this is just general integers, but I impose that s must be co-prime to p because I want things to be invertible in z mod p to the L. So z tilde p is a subring of q. And so this is a construction which is kind of very, very similar to what we did in the case of rational numbers. We started with integers, we got rational numbers as these kind of tuples. And what we are saying is, in this case, I don't want to add inverses to all the elements. I will not, but I will save one number, which is this p, from being invertible.
What is the valuation? इसके element की valuation क्या होगी?
अभी तो कोई valuation नहीं, but this valuation still works the same way, right? That comes from, yeah. So the q. So in this case, I can just write q is p to the r times q tilde, and the valuation will be this r, right? Because s will be co-prime, there will be no factors in the denominator.
So that's why valuation अगर कोई factor भी common नहीं है ना q और s में, कोई common नहीं है.
अगर
s
oh, you want the valuation of this thing, q, the addition.
the addition की नहीं q over s की.
Q over s key, so this will be just the valuation of q, because s is co-prime to p. Yeah. Because valuation is multiplicative. So this has 1, valuation 1. So no, valuation is, sorry, additive. So valuation of this is 0, so not 1. The valuation of s is 0. And so this is a subring of q, and we are kind of like in a very similar place to where we were when we started working with rational numbers. So this is not a field because p is not invertible, but otherwise it's a pretty nice space. But what it is not, so there is a metric. So p-adic metric gives us a distance on z tilde p, but this space is again not complete with respect to this metric. So what I have done, if you kind of so this kind of thing I can do pretty generally. In this case, I inverted all but 1 primes. I can also take a smaller subset and invert those, and this construction will still work, except I will probably not get a very nice distance. But since we have a metric, I can do metric completion. And this set, yeah, so this zp, so this set is exactly the metric completion of this guy, right? So if I stop after a finite number of terms, I will get something here, and or if again if there is some kind of periodicity in the coefficients, I will get something here. This is how rational numbers work in real numbers in let's say base 10 expansion. So I will have the same thing if there is some periodicity in ak, or I mean if they become 0, that's also periodicity, then I will get a rational number. Otherwise, this series does not correspond to such an element. So this is just is the metric completion of this space, and this space is nice because on this, so there is a map, and so let me write. Okay, let me erase this, and so there is a map mod p to the L, and L can be any integer here, and this map goes from this z tilde p to z mod p to the L, and it works in the obvious way. And the reason, and we have almost constructed this, not almost exactly constructed this z tilde p as the largest subset of rational numbers on which this map makes sense. So this gives me, so this is kind of like I want to like come back.
So if you are saying this is a map, you are talking about like map as a rings.
Map as rings or groups, works for both, right? So because
What would be the zero divisors in that P?
Z, Z, no, so there are no zero divisors here, but P is not invertible.
Okay.
So this is not a finite. This is not a finite ring. So there are no zero divisors. But the only thing is there is no inverse of P. So if you add the inverse of P, you get back to Q, right? So you will get back to Q. You complete that with respect to p-adic metric, you get QP. So here the only thing we have done is not added an inverse for P, so that this map makes sense. So if I add an inverse for, so the zero divisors are here, but
Actually, more than I think it is a local ring.
Now visible is
ये local ring के बड़ा है.
actually यहाँ पे I think so it's like
ये localization है prime
Yeah.
model generated by P पे.
so it's localization of everything except P.
हाँ, prime
Yeah.
model generated by P.
Yeah. So okay. So we have this map, and this is very good. So this map extends to a map on ZP in the obvious way, right? And so this extends to ZP, and how? So I can just say let me go to I have a p-adic number which is a naught plus a1p plus a2 p square plus so on ak pk. So I can, so this, let me call it again Q. So Q is A0 mod P. So in case of L equal to 1, I get A0, and Q is similarly A0 plus A1 P mod P square, and Q is A0 plus A1P plus A2P square plus AK, and then P to the K mod P to the K. K plus 1, yes. Thanks. So this, and the nice thing here is, so this again, I can take this, so let me define this thing as QK, and the nice thing is that if I have some K prime, so QK is same as QK prime mod Pk prime plus 1 if K prime is less than K, right. So I can take, I have this, I can reduce it mod P, I get A0. Similarly, if I have, I can reduce this thing modulo K, and I will get QK minus 1. So another way, so this gives me another way of describing another way of describing p-adic integers or the elements of this set were ZP. So, so any p-adic integer written as, so I can write it as a big tuple. So, the first one is this is A0, which I called, I think, Q0, Q1, Q2, and so on. So, this is an infinite tuple provided such that Qk, so if I take Qk mod, maybe Qk is same as Qk minus 1 mod p to the k. So, I want Q2 to be Q1 mod p square. So, if I take Q2 mod p square, I get Q1. If I reduce Q1 mod p, I get Q0. And this I can so what I have a sequence of finite groups. So, this sequence is ZP and then ZP square, ZP cube, and so on. And what I have is, so again, so let me Z p to the k, Z p to the k plus 1. So, always I have this map. Similarly, there is a map here. And this works by reduction. This map works by reduction. And I can define, so there's something called colim, which is just saying, so what I want is I want an element. So, there's a group. So, there's a sequence of groups. What I care about are these maps in this direction. And what I want to do is I want to describe an element of this sequence of groups. So, if I have two such sequences, I can multiply them in the obvious way. I can add and multiply them. So, I can even consider them as sequence of rings. And I want to define a bigger group that captures all these maps. And this is obviously this p-adic integer and is such a p-adic integer. So, this is an infinite tuple of elements. So, this kth element corresponds to this qk, and when I reduce it, I get the previous element. And the only reason I have to think of this sequence instead of finding a single. So, if these q's stabilize at some point, I would have a finite sequence, but they don't, right. So, the groups are become strictly bigger and bigger I go on that side. So, I cannot describe I cannot really use a finite amount of data to describe this element. And this is kind of the reason why we had to do the field completion, right. So, these maps make sense. So, these maps make sense over Z tilde p, but I will not get all the elements here in this sequence if I just restricted myself to Z tilde p. And the metric completion basically ensures that I get every such sequence, right? Because this reduction. So again, so as we go further and further, the distance between any two elements of this any two elements in this sequence is very, very small. And this is actually kind of a Cauchy sequence. This is exactly like a Cauchy sequence, but with a p-adic distance. Okay. Okay, so we have this this idea of p-adic integers, but and this is, if you want to give me a p-adic integer, you have to give me one element of z mod p to the k for every k. And there is a consistency condition that tells which is this one. So now I want to use this to be able to do something, and that something is kind of the question that led us to rational to real numbers last time, right? So last time we tried like, okay, so there are two equations, x squared plus 1 is equal to 0, and then x squared minus 2 is equal to 0. Right, so these equations have no solutions in rational numbers. We saw that this one still doesn't have a solution in real numbers because the distance between any solution of this equation and any rational number is large. This is not the case here. So now we have a different notion of distance. So it's not obvious which of these equations have a solution for p-adics, which one don't. And what we want to do is now is kind of investigate which ones, when do these equations have a solution, right? So the first thing I can do is okay, so this is too big a task, but I have some simpler groups which are closely related available to me. So what if I reduce this equation mod p? Right? So if there is a solution over p-adic numbers, there is a solution over mod p. And in fact, we can do something general. So let me for now just focus on this equation, the first one. So if x squared plus 1 has a solution in is equal to 0, has a solution in Zp, it has a solution in Z mod p to the L for all L, so all integers bigger than 1 or equal to 1, right? So this at least gives us a necessary condition for a solution to exist. And I can try some, so I can try the first few primes. So Z2, no, okay. Like I said, I will do it. So Z mod 2, so this has a solution which is 1. So x is equal to 1 has a solution. Z mod 3, there are only the only options are 0, 1, 2. 1 square is 1, and 1 plus 1 is not 0. 2 square is 1, also 1. So there is no solution. Is the solution. So I already know that this equation has no solution over Z3, which is the group of p-adic integers with p is equal to 3. So what about Z mod 5? And there are two solutions, which are 2 and 3 are solutions. So 2 square is 4, 3 square is also 4. And so generally, what happens here is, so there is a solution is a solution to x square plus 1 is 0 mod p if p is equal to 1 mod 4 and no solution no solution if p is 3 mod 4. And this comes, I think in this case it's actually pretty easy to write down the solution. It's probably something like I don't take me my word because I'm not going to write it, but I think it's going to be probably something like this. But I will need to check, and I don't want to do it right now. But it's pretty easy to find this solution. There is also like a general phenomena which is called quadratic reciprocity, which is what controls the solutions of quadratic equations modulo p. But and what quadratic reciprocity tells us that the solution of x square is equal to something mod p is related to the solution of x square is equal to p mod something. So they are related, but I will not go into this. For now, we will just like take it for granted that in this case they are solutions, in this case they aren't. And at least for the next case, which is 7, pretty easy to check. There will be no solution. For 11, there will be one. There will be 2. I mean, if there will be 2, because if x is a solution, minus x is also a solution. Okay. But the question is, do these solutions actually give me any solution over p-adic integers? Right. So, and a solution over p-adic integers is just because of this. What I want is a solution over z mod p square, then a solution over z mod p cube, then a solution over z mod p 4, and so on. So, we will just do this order by order in p, right. So let's just do like maybe one example, which is this z mod 5. So 2 solution in z5, I can go order by order in p to the k, or in p maybe this. So next thing I want to do is, so there is a solution, there are 2 solutions in z5, so which are 2, 3. So if there are solutions in z mod. So if there are solutions in z mod 25, they look like so there are 2 possibilities, and one case is let me write, so x is let's say a times p plus 2, or x is equal to b times p plus 3. And this is because I still have the reduction map. So if I reduce it mod p, I should get back the solution I had before. And there I had 2 solutions, so these are the only 2 possibilities. And these a, b are again, I can restrict them to be in the set from 0, 1, p minus 1, right. Because if they are bigger than p, the value mod p square will be the same because this p is already present. So, let us try to solve this using this ansatz. So, what I want is a times p plus 2 square is 0 mod p. Plus 1, yes, thank you. That plus 1 is very important. And this tells me that a square p square plus 4ap plus 4 plus 1 is 0 mod p. And this is kind of the nice part. So, this thing is 0 mod p square. So, although before I had a quadratic equation, I am left with only a linear equation now.
So you want mod p square, right?
Mod p square, yes. And this thing I can write. So, and this p is 5. So, maybe I should have written 5 everywhere. So, this is 25, 25, and this is 20a, and this is 25a square. So, this is 0, and what I get is 20a plus 5 is 0 mod 25. And this thing, as you can see, so there is a factor of 5 here, there is a factor of 5 here, and that just is telling us that we started with the solution modulo 5. So, I can factor out this 5, and this tells me, so a solution to this equation is the same thing if I divide both these by 5, which I can do because they are both multiples of 5, and this is 4a plus 1 is equal to 0 mod 5, right. And the solution is no, it is not invertible, but both of these have multiplicity 5, and I only care about a solution between these. So, what I am saying is just solve this equation, which you get by just because both of them have a factor of 5, I can divide by 5 here. So, this is like just take any integer left, there is an obvious one, then you can divide by 5, solve that equation, take the solution modulo 5. So, but I think I made a mistake. Did I make a mistake? Because here what I am getting is a is equal to 1, right, and 36, and 36 is not what mistake did I make for 10. So, this is 10. Oh no, so this is ये 10 था नहीं 22 times no, I think it's probably correct, and oh yeah, so the solution is a is equal to 1, right, and but the problem is, oh yes no, it's correct. So what I get, so my solution mod 25 is 7 square is 49, and 49 plus 1 is 0 mod 25, right. So we are good, and this is kind of, so this is basically the thing that makes it possible. So here we only had to solve a linear equation, and the linear equation, I had to solve linear equation in a field after using the fact that there are some common factors. So, and linear equation in a field is always possible unless this coefficient is 0. In this case, it is not 0.
So the solution is 25,
7. So this is 7 mod.
So can you write over this?
Yeah. So similarly, so actually I will go there. Yeah. Yeah. I will write. So I will write down here. So there are two solutions. One is 7, the other is minus 7. So 18. And So mod 25, the two solutions are 7 and 18, and 18 is just minus 7. So, it will obviously solve the same equation. And the other thing I want to kind of notice is that this is basically, this solution is unique because I have a linear equation, and it reduced to an equation mod 5. In general, I'm not even I'm not guaranteed that things mod 20 polynomials mod 25 have a unique factorization. But in this case, it's happening, and in some case we will see it's kind of related to the unique factorization. In ZP, at least it's a necessary condition for that to happen. Okay, so let's go to the next step, and so let's look for solutions mod 125. I will just focus on the one that reduces to 7 mod 25. So, a solution, so and of the form which looks like (25). So, x is 25a plus 7. So, again I know what my solution should look like mod 25. So, it must take this form. 5? 5d?
I mean 25a plus 7 or?
Yeah, because if I reduce it mod 25, I should get 7, right. So, this is what the only two solutions are 7 or yeah.
125 कम कर रहे हैं
हाँ.
नहीं वो using 7 को reduce नहीं कर रहा 2 में.
Yeah, it's 7 is yeah. So what I should get? So, x square plus 1 is equal to 0. This tells me that 25a plus 7 square plus 1 is equal to 0, and maybe mod 125 mod 125. So, now I will be quicker. So, there will be I think like 25 times 5 is 25 square is 625, that will be 0. So, I can forget about the quadratic term. So, then the other one will be, I think this is 2. So, I think it will be 100 a. So, this is 2 mod. So, I only care. So, when I am multiplying it, I only care about 7 2 mod 5. So, this will be 2 times 25 times 2 100 a, and the last term is again 49 plus 1 0 mod 125. And here again what I get is 49 plus 1 is 50, and 50 is 0 mod 25. And this is again, so I get factor of 25 here, factor of 25 here, and what it is saying is that I started with the solution modulo 25. So, my equation is trivial mod 25, but it is non trivial mod 125. And this, so this time again what I have to solve is an equation mod 5, and the equation mod 5 is 4a plus 2, right, is equal to 0 mod 5, and the solution here is what is the 2, yes. So, a is equal to 2. So, the solution is, so mod 125, the solutions are so 25 is 50. So, 57 and minus 57, which I guess 68. So, and this process I can continue, and Yes? Okay. And so instead of kind of trying to continue it for this example, let us try to do it somewhat generally, right. But the idea is the same. We will assume there is some solution. So, there is a polynomial and it has a root mod p, and what we want to do is to lift this root to higher modulo higher powers of p. And this fact, this thing is called Hensel's. So, this general phenomena is called Hensel's lemma, and what it says is this. So, suppose a polynomial let us say p of x has a simple root modulo p, and so a simple here just means it is not repeated. So, it has multiplicity 1, simple root. So, let us say what should I maybe r has a root r modulo p. Let me name it r1. Then and let me say monic here. So, this is not too important, but it is somewhat important. And this polynomial is a polynomial with p-adic coefficients. So, general p-adic coefficients, but I want it to be monic. It is not too important unless the first coefficient is p, then it causes some problems, but we will take it to be monic. And so, then there are let us say x k in z mod p to the k plus z mod p to the k such that p of x k is 0 mod p to the k. So, this is the saying. So, I get a root mod p to the k for all k, and x k plus 1 mod p to the k is x k. So, this root reduces as we expect it to.
So, the coefficients of the polynomial you said are in p-adic
Yes.
rational?
No, integers, p-adic integers.
P-adic integers.
Yeah. So, this let me just say this is in is a polynomial with p-adic coefficients, but in p-adic integers.
So,
If you can remind me what the p-adic integers are.
So, they have a p series without any negative powers of p.
Oh, okay.
Yeah.
so maybe I'm just confused.
Hmm.
You said that if you have a simple root in p-adic numbers,
Yeah.
then
No, mod p, simple root modulo p. So, this is like z mod p. So, simple root is in z mod p, not
z mod p.
z mod p.
Okay.
So, the coefficients are in the p-adic, but the root is.
So, I can ask. So, I do not know. So, I do not know if it has a p-adic roots or not. So, what I am saying is, okay, a simple problem is find out if this polynomial, so the mod p reduction works. So, what I can do, simplest thing is try to find the root modulo p. And what this is saying is, if you can find the root modulo p, you will be able to find a p-adic root, and you will do this by there will be a root modulo p square, another root modulo p cube, and so on.
So the root in p-adic
Yes.
the root in mod p.
No,
And the root is simple.
you guaranteed a root in every mod p mod k pk.
That's definition, right? That's the definition of a p-adic root. But this is saying if you have a simple.
That's the my confusion. I mean, that's not the definition. You say that that's the necessary condition, but not the sufficient condition.
No. Root modulo p is a necessary condition. But if you have a root modulo p to the k because of the co-limit, that's same as saying that you have a p-adic root. Okay. But this is saying that, okay, so things are not so bad. If you have a root modulo p, you will get a root modulo p to the k for all k if this root is simple at least. Okay. If this it is not simple, then things then the root might or might not exist. Okay, so you have this root modulo p to the k. It reduces. So if you take the root mod the k, if you take the root modulo p to the k plus 1, reduce it mod p to the k, you will get the previous root you did. And xk plus 1 is the unique such root in Z mod p to the k. Oh, k plus 1. Right? And this uniqueness is important because p-adic integers, they have unique factorization of polynomials. And what I'm saying is no matter which root you pick modulo p, you can lift it. So if the uniqueness is not there, I will be able to get two different factorizations modulo in ZP or p-adic integers. But it's also like falls out pretty simply when we try to solve this. When we try to solve this, when we try to prove this, and the proof will go exactly like this. What we will have is so we are given a root modulo p, and then we will try to write higher. Then we try to find these other roots. But this is an inductive process, so I am given the base case. So what I want to do is, if I have a root, if I have this x p of xk, I want to find p, the next one. Okay, so given xk like this, if xk plus 1 exists, then xk plus 1 will take the form p times a times p to the k plus xk. So again, so if I reduce this mod p to the k, this will disappear. I will be left with xk. And this is just saying, okay, I'm just also using this property because I want to show that there is a unique root with this. Uniqueness I don't need to show, but it will be there anyway. So what I want to show is I want to find A such that P of A is equal to 0 mod p to the k plus 1. So, here I have, so I want to do something like that disappearance of some factors that happened due to squaring, but here there are more powers. But there is like a pretty standard way of wanting to expand around this xk, right. So, I can just use derivatives, and derivatives work in polynomials the same way as they do in real numbers. They are coefficients, so derivative k minus 1, and I'm going to use this. And so, what I can do is I can expand around. So, I can expand this around x to the k, xk. So, p to the, so p at this point is equal to p at xk plus the difference is this a p to the k p prime xk. The next term is a p to the k square, and second derivative at xk. And now there are more terms, but I do not care. So, I can see that this one is 0 mod p to the k plus 1, and all the other terms are also 0. So, but here there may be another comment that I should have made earlier. It is not actually necessary that I go 1 up in power. I can double the power 2, and this thing will still be 0. So, what I'm doing is, I think it's called like linear lifting. So, which says go up, find a solution which works modulo p to the k plus 1 from the one that works modulo p to the k, but you can also just go to a solution modulo p to the 2k directly, and that is because this term will vanish up to that point. So, this term will still be 0 modulo p to the 2k, and nothing much will change. So, the equation I want to solve now is the one. So, is p to the, so p at xk plus a times p to the k, and then p prime of xk is equal to 0 mod this. And here again I have the same fact, there is a factor of p to the k. So, the I only care about a modulo p, and I know that p at xk was a solution modulo p to the k. So, this thing is a number times p to the k. So, since p x k is 0 mod p to the k, there is, so xk, no, so p to the, so p at xk is p to the k times b for, and I can for some b in 0 1 p minus 1. And so the equation I want to solve is again very simple. It is just a linear equation which looks like b times p to the k plus a p prime x is 0 mod p to the k, and this is same as a solution to b plus a p prime x k, but mod p. I want a solution mod p to the, no, sorry, mod p to the k plus 1. I already have these vectors of p to the k, but the only thing I want is a solution mod p to the k is exactly mod p, and this solution will exist unless this p prime of x k is 0. So, unless p prime of x k is 0, there is unique solution, but if p prime of x k is 0, then the root was repeated. But if 0 x k or like x 1 mod p was not a simple root, and we are done. So, we have shown that if we have simple roots mod p, then the polynomial will have roots modulo p-adic in it will have roots in p-adic integers. So this can be, so this is kind of like a very basic version of Hensel's lemma. It can be generalized in multiple ways. So the first thing is what if my polynomial does not have some root mod p, but it does factorize in some way, right? And there is a generalization that says that the polynomial will factor kind of the same way over p-adic integers as long as there are no repeated factors. But and this is something maybe I will come back to next time, but since I think we still have time, or
Yeah, we have time.
okay. So today I can maybe like try to discuss a generalization of this thing in another direction, which is what kind of rings, so what are the kind of rings for which this kind of construction still makes sense. But for that we need to talk a bit of ideals. So I will kind of like give a very quick introduction to something about ideals and explain what a maximal ideal is, and it basically kinds to give rise it give rise to things which are very closely related to p-adic integers. And okay, So where was I? Okay. Here. So we have a ring R, ring, and for me it will be unital commutative ring, and that I want to get out of the way because I will keep forgetting to mention it. Okay, so R is a unital commutative ring. I is an I, which is a subset of R, is an ideal if it satisfies two conditions. So I is a subgroup under addition. So what this means is that if I add two numbers, if I add two elements of I get another element of I, and 0 is here. And the other thing I want is if S belongs to I and R is in the ring, then RS is in the ideal. So this is a bit stronger condition than just saying that this is a subring, right? So subring would just say, okay, if both of these are in the ideal, then the product should be in the ideal, although that, but this is a bit stronger condition. And the reason we want this is, so if then, so given an ideal I, we can define another ring R mod I. And this is, if you know quotient groups, this is some generalization of quotient groups. And what are the elements? So the an element which for some reason is denoted maybe something like S plus I is a set, and this is the set of elements of the form S plus, no, so R plus I, so R plus S, where S is in the ideal. And addition and multiplication kind of follow as you, so we can try to write down the most naive version of addition and multiplication, but maybe before that. So again, this R, so since this R is an element of the ring, it does not uniquely label this element, right? So R plus I is same as R prime plus I if R minus R prime is an element of the ideal. So they give me the same element. And so I have to, so I can again, so this is like mod P. So what I am saying is identify those elements in your ring that differ by an element of the ideal. And so then on this set of equivalence classes, I can define addition and multiplication. So, R plus, so if I have this set and so I define the addition to be I. Similarly, is so if I am defining them like this, I should worry a bit, because I am picking these representatives out of thin air, and so maybe if I change the representatives I have used, maybe this thing will also change. So what I want to say is, so if so what do I want to say here? So the first one is pretty easy. So if R plus, so if R plus I is same as, let me why did I, is S plus I, then I know that R minus S is in this ideal, and similarly if R prime plus I is same as S prime plus I, then R prime minus S prime is here. So if I use these two, so if I use these, if I use S and S prime to write down this these two elements of my ring, then I will get the answer which is S plus S prime, right. So, but S plus S prime is equal to, what I know is that, so S is just S, so R plus R prime minus R minus S plus R prime minus S prime, right. So this R prime cancels here, and so S plus S prime plus I will be same as R plus R prime plus I, because I am just shifting by this element which belongs to my ideal. And this is simple enough. So the same thing I need to do with multiplication, and there I will actually need this. So here I only needed, okay, so I have two elements of the ideal, I needed to add, I only needed the elements of the ideal to be closed under addition. But if I try to do multiplication, it's not enough. And so so addition from, so now let's come to multiplication, and what I have is R and S describe the same element of R mod I, and similarly R prime and S prime describe the same element of R prime and S prime describe the same element. So consistency requires that R prime minus S prime is in my ideal. So I can get two different answers. Seemingly I can get two different answers using different representatives. What I want is that they describe the same element in my ideal, and what I want is this what I use is this property. So what do I do? So the only thing I can do here is again split this into r prime minus what is in my ideal. So r prime minus s prime, and then there is, so I have no, what is, so r prime minus ss prime, and this I can write as r, and then r prime minus s prime. So now I have added r s prime, and then minus I should write s as r prime so what is the other one, r minus s, or maybe no, s minus r times s prime. So here there is a cross term r s prime, here there is a cross term r s prime. So I have written the same thing, but so I know that r prime minus s prime is in my ideal and s minus r is in my ideal, because but these r and s prime themselves are not necessarily in the ideal itself. But what I do know is that if I have an element of the ideal and any element of the ring, I get something in the ideal. So r prime minus ss prime is in this ideal. And so we have, so now we have some notions, some notion of rings which look like Z mod n. So the ideals, so ideals of Z are nz, which we define to be n times set of all numbers n times m, where m is any integer. So these are ideals. So these are obviously closed under addition. And if I multiply any number which has a factor of n with anything, it will still have a factor of n, as long as I stay, I mean, in integers this is true. So Z mod n, so the rings we were talking about earlier, are examples of R mod I. And okay, so this is, so we have some examples of R mod I, but what I would like is an example. So what I would like is a generalization of Z mod p to the L, right? So this is what we needed to define our sequence of rings on which we applied this kind of Newton's method due to Hensel. So I want something like this, and although I have this Z mod n here, so I know how to understand Z mod n, I do not know how to understand Z mod p to the L unless I think of my very specific ring which is integers, because here I don't see really an operation of taking powers. But we can do this, and so we can define, so if ij are two ideals, then I can define two more ideals. So, that this I plus j I can write as maybe S, the set like this, and S belongs to I, T belongs to j. So, it is like k take 2, add all possible take all possible sums of elements of I and j, and this is an ideal. It is pretty easy to show, and so I will not go through this. The other one is I j, and here things are a bit more messy than here. So, what I want is what I would want is, okay, the elements are like products of elements, an element here, but that does not close in the addition. So, what I do is I just make it close by hand. So, the elements here are like I, maybe let us say 1 to n, and Si plus Ti, and Si are here, and Ti. Oh, yes, sorry, product. Yes, sorry. Yeah, otherwise I would get the same thing as S plus T. Yes, thank you. So this will be the product. So, this is again, this thing is an ideal. So here, so the non-obvious thing here was the addition, and the addition I have put by hand. So, if I have a finite sum of the products, I add them, I will get a finite sum of the products. So now I have something like z mod p to the L. I can define z mod I square, I cube, so on. So, here maybe like kind of just to orient ourselves. So here, so I plus j always contains I, and it will contain j, right. So, I can just fix t to be 0 here, and I will get all the elements of I. And but I plus ij can either be bigger or smaller than I or j, and we can find examples very easily here. So, if if I have z, so if I is, let us say 2z, j is 3z, you can check, because of again there is a linear combination of 2 and 3, which is 1 mod 6. So there's a linear combination of I and j, elements of I and j, which is 1. So 2z times 3z is integers. So, you get all integers as finite linear combinations of elements, which are multiples of 2 and multiples of 3. But if I have, maybe I will go here. 2z plus 3z, is it? Oh yeah, no, yes, this is true. So, this is 6z. So, 2z, yeah, I was wrong. No, I think this is true. Plus, but you can, if, oh yeah, 6z. No, this is 6, yeah, this is true. 2z times 6z is equal to 6z. So, yeah, I was 6. oh 3z, right. So, yeah, so here I will get everything will be will have 6 as a factor. Yeah. Okay, so you will get 6z.
And
Okay.
2z plus 3z is equals
To 6z, yes. So linear combination is there. So, but more important for us will be like, so z mod p times again z, pz, product of pz is p square z, and there is the same thing. So if S is a factor, has a p as a factor, T has p as a factor, I will get multiples of p square. So the thing, so we have some, so I can pick any ideal I and consider the sequence, maybe R mod I square, R mod I cube. So the problem right now is at the bottom, I will like to have a nice field, and generally this will not turn out to be, R mod I will not turn out to be a field. So in our fields, solving all equations is easy. I mean, it's not trivial, but at least is easy compared to doing it over a general ring. So what I want is a field. So that's, so if, so at least a sufficient condition is if, so an ideal I, which is not the whole ring itself, is called maximal if any, if the only ideal that contains I is R itself. And if I is so we will show this now in a little bit. So if I is a maximal ideal, then R mod I is a field. And so this works pretty nicely then. So and what we have done, so we can ask about maximal ideals of integers, and those are precisely those which are of the form p times z. So for z, the maximal ideals are pz, where p is a prime. So let's see, let's come back to this. So here at least it's pretty obvious, z mod pz is a field, and the way this works is more or less that if I look at all the numbers of the form, so if I have, so let's see how it works here. So if I have an integer, and I have another, and I look at and I look at all so I look at all products. So, look at all numbers, integers as n m. So, I go over all integers n m. So, then what I want is, so there is again there is a q. So then because n and p I can take them to be co-prime, then there is a q such that there no. So if n belongs to z, there are m and there m and q such that n times m is plus p times q is equal to 1. And then I say, so in this case what happens is that n plus pz has as inverse m plus pz. So this is what this equation is telling me. Okay. So what we want to do is to generalize this process. So we already have a ring R mod I, what we want to check is that inverses always exist. So I do the same thing, and so the only thing I can use is that this ideal is maximal. So I want to construct some other ideal, and this ideal should contain this I, and it should be strictly bigger. So if this is strictly bigger, then this my new ideal is strictly bigger than this ideal I, then it will contain 1, and this is more or less what I want, right. So what we do is, so given, let us say x plus I, consider the set, let me call it I tilde, which is a set of all elements of the form x times let us say y plus s, and this y is, so y goes over all the elements of my ring, but s is in the ideal. So this y is the thing which should give me the my inverse. So let me, okay. So one thing we want to check is if I have two elements in this ideal, the product is also in the ideal. So not product, sum is in the ideal. So if I have, so x y plus s plus x y prime plus x y s prime is obviously just x times y plus y prime and plus s prime, and this is in the ring and this is in the ideal. So we are safe. Similarly, if there is an element of the ring then what we have is that r times x y plus s is x times r y plus r times s. This is again in the ideal because I tilde, sorry, I. So, this is in the I, and this is in the ring. So, I tilde is in ideal, and now I can just here I can fix y to be 0, go over all the elements of the ideal. So, I get I. I tilde contains I, but it might be exactly I. And but here, so I have so x plus I. So, if x plus I represents a non-zero element of my quotient ring, then this x is not in the ideal. So, and I can set y to be 1, s to be 0. So, x is in I tilde, but x is not in but x is not in I. So, if x plus I is not equal to 0, then x is not in I, but x is in I tilde. So, what I have is a strict inclusion. So, I tilde contains I, and this means since I is maximal, I tilde is equal to R, and 1 is in I tilde. And now I am almost done. Where is the cloth? So, if I pick, so what this means is there is a y, there is a y, and no, there are y and s such that x y plus s is equal to 1. So, because 1 is in my ring, so this means x plus I times y plus I is 1 plus I. So, I have an identity. So, I have an identity here. So, this y we found this way is the inverse of x. So, now we also have a field, and
so maximal ideal, so if you take a constant with maximal ideal, you have a field.
And so the examples of this are Z mod P. Okay. So, we have more or less all ingredients of running through the process that we went through Hensel's lemma, right. So, we have but before that, this kind of like I will not go through Hensel's lemma again, but we can have like a very similar construction like we did for like we had of p-adic integers. So, what I have is an ideal. So I have some ring. So I have R mod I. So this is a field. R mod I square. This will no longer a field. It will, and in fact, it will have 0 divisors, right. So if this I and I square are not exactly the same, and so what I can see is, so this I square, so this I square is sum of finite combinations, is a sum of finite sum of the products 1 S I T I, and these T I are in I. But since the ideal is closed under operations of both addition and multiplication, so what is pretty easy is I square is contained in I, and similarly I cube will be contained here, and so I have this chain, and when I do the quotient, the opposite thing happens. So what I have is there's R mod I, and this is contained in R mod I square.
Map over reduction map.
There is oh yes, sorry, yes, sorry, no, yeah, sorry, there is no subset relationship between quotients. So there is a map which goes from I square, and how does this work? So so some elements of I, some elements of I, so the elements of I that are not elements of I square will give me non-trivial elements. And if the reduction map basically says that so it's get rid of all those. So reduction map just says, okay, go through the identification we did when we defined the ideal. So and so on. And so on. So there is this reduction map, and what this allows is, so one thing we can do is to do what we did for what we did for to get p-adic integers. We can define the co-limit of this process, and that defines an analog of ZP. But we can also like kind of, so this is, yeah, so, okay, so I will finish in 2 minutes. But we can kind of do the same things as we did in the case. We can also do something which we did in the case of p-adic integers, which is we can define some kind of idea of a distance between different elements in this field, which we get as co-limit, right? So how did that work? There, So, we had similar inclusions Z mod p Z mod p square Z mod p cube and so on. So another way of looking at the distance we defined was, okay, the elements which reduce to non-zero elements here, they have distance from 0, which is 1, right? And elements, so elements which don't, so the elements here which reduce to non-zero elements here have the same distance, but the ones which do reduce to 0 here will have a distance which is 1 over p. So, the 1 over p distance are exactly those which reduce to 0 here. Similarly, here the elements which have distance 1 over p square are those which reduce to 0 here. So, I can do the same thing, and so if I have an element which reduces to a non-zero element here, it will have, I can say, let's have a distance, it will have a distance, I don't know how to pick exponent here. So, let's just pick like 2. So, it will have distance 1, and the elements which reduce to 0 here will have a distance 1 over 2, next 1 over 4. So and I can again kind of do the completion with respect to this idea of the distance, and so this is normally, I think, like done directly in, not in terms of distance, but in terms of topology. So there is a topology, and this is called p-adic topology, but it's doing the same thing. What it says is that the open sets are so open sets around 0, so which contain 0 are these ideals. So this ideal I, this ideal I square, I cube, I 4, and so on. And I guess I will stop here. And this very natural, generally, like in this setup, we can generalize the Hensel's lemma a lot, because most of the ingredients that go into showing it are already there. And so this will maybe make sense. Okay.